Hi everyone, this is going to be a video to explaining the shapes of the graph of a polynomial functions around the zeros, and we definitely use these subtle differences according to the multiplicity of the linear factor. We use those properties to sketch the graph of polynomial functions. Rather than writing down the general form, general factored form, I will just use this three-factored linear factor with a different multiplicity, so that's complicated enough. So let's look at this polynomial px with the three distinct linear factor with this multiplicity to that. So goal is that if we happen to have a polynomial in this form, how are we going to sketch the graph of the function, especially doing something a little bit accurate around how it's going to cross the c, which happened to be the one of the zero, how it's going to cross b, and how it's going to cross a according to the multiplicity here. So these are all unknown and not really distinguished. I'm just going to focus on this c and with the multiplicity m, and I'm going to introduce this table and explain why it works like that. So here's an example. When the multiplicity of that factor x minus c is 1, then the way the graph of the polynomial crosses that zero is going to be this shape, where this is x-axis, or it's going to be that shape. It's kind of, cutting through. When the multiplicity is even, the power of x minus c greater than 1 is even, then it's going to be either this shape that's staying above the x-axis and staying below the x-axis, just touches and remain on the one side. So finally, if it is an odd multiplicity, and therefore has to be, but it is greater than 1, not 1, then it resembles like the graph of y equals x cubed. It's either this shape or that shape. So the question is that what determines either this or that is obviously this table says that multiplicity determines this shape, but this flipping part is determined by what is happening around to the other factors, not the x minus c. And that's the interesting part. Right, let me use the example to explain how to use that information to sketch the graph of this polynomial function, for example. So I wrote these in. These is the one of the 0, 1/2, relative located here, and the other 0 is 2, so relative located there. -1 from that factor is located here. So because its leading coefficient is positive, we're going to start from here. So we're going to start from here, and when we cross this x equals 2, then its multiplicity is 3, so it resembles the cube monomial y equals x cubed, but it's centered around this x equals 2. So it goes like this. So I sketch it over here, more or less resemble this cube part. And of course this part continues continuously going up like that. So it's going to have to turn around to cross this 1/2, but the multiplicity of 1/2 is 1 here, so therefore it's going to cross this way. And the reason it's going to cross this way is kind of obvious because we're down here. So I'm going to continue from here. So that's the one shape is going to cross over. Then you have to come down and cross this -1, but -1 came from this factor, and its multiplicity is 2, so it's going to lift up. So we're going to continue from here. So it's going to, the shape is going to roughly, it's going to look like this. So that's how you use that table to sketch the graph of the function that looks given by this factored form with this multiplicity. So let me explain a little bit more about this near zero behavior. So let me use this space here to explain a little bit more about the near zero behavior. So I'm using this symbol, wiggly equal symbol, that means x is not going to be exactly -1, but it's very, very close to -1. And we're going to use this expression. When x is very close to -1, this factor is going to be very, very close to 0. In this factored form, if there's a 0 in there, that kind of kills everything. So we will keep that factor, which is the main factor that tells us how the shape of near 0 is going to be. But this part and that part, if x is very close to -1, it's going to be a non-zero number. It's very close to a non-zero number. So here it is. If x is very close to -1, if you place x equals -1, that's -3 here. that means this factor is very close to negative 3. Not exactly negative 3, but some number that's very close to negative 3. So px is not exactly equal to that, but it's kind of close to that value, negative 3. If you also do that to the same thing to this factor, x is negative 3, that's negative 3 raised to a third power. So this whole expression is kind of very, very close to this expression, where x plus 1 squared is the important factor, and together is a positive 3 raised to the fourth power, which is 91 and 81, and x plus 1 squared. So if you think about this factor, that's exactly the quadratic monomial shifted to the left by 1 unit, and with this large coefficient multiply, leading coefficient. So that definitely a concave up shape there, right? So I actually used computer software to compare the actual graph of px with this 81 x plus 1 squared. So let me show that part. Right, this is the graph of actual polynomial generated by computer software, and this is in the correct scale. The length of this one is exactly equal to the length of this one, and that's shown in the correct scale. That's actually how the graph looks like. So x equal negative 1 is here, and graph shows that it is kind of y equals x squared. That 81, the large coefficient, explains kind of how it's growing, how narrow this part of the quadratic formula is. So this is the following is the comparison with the actual graph with the quadratic approximation we came up with. So the quadratic approximation is in red, the actual curve is in blue. So it's very difficult to see because it's almost the same around here, but if you go over here, you can see there's a red part coming out, and it becomes slightly different as we move further away from x equals negative 1. This is the picture a lot more zoomed in, so you can kind of see that discrepancy between the red, that's approximation, and the actual curve that's in the blue. So that's this part right here. That actual graph is well approximated by square shape. So that's how the table I showed earlier, the shapes near 0, it's coming from. If you have this even degree, that's going to resemble very much about this quadratic function monomial part shifted to the x equals negative 1, which is this one here. And also whether it's going to be a concave up or down is determined by this coefficient, and from here they came from the other linear factors that is not equal to x plus 1. So let's do the same thing around x equals 1/2. That's the second smallest 0. So I'm doing the same thing. The px, I'm using this form, and this is the factors contributing to everything to 0. So we only plug in x equals 1/2 here. So that'll give you 3/2, and that's going to be 1/2. This is 4 halves, so that's going to be 3/2. So if we put them all together, this coefficient turns out to be this large coefficient, and this 2x minus 1 is that linear factor we're keeping. So the slope will be this 2 times this number outside. Because it's linear, it's going to be simply a line. So that's the shape. So that's negative 243 divided by 16, and that's roughly in decimals negative 15.18. So it's fairly steep a line. So like I did last time, I'm going to go to the computer and compare actual shape of this graph with this the linear kind of approximation there. Alright, this is the picture. This again, the blue is actual curve, and our linear function is this part here, and you don't quite see here, but you can see there's this line cutting through. So there's this line that is approximating this part very, very nicely. Actually, this line is called a tangent line at that x-intercept. That's exactly the tangent line at the x-intercept. So this is the main subject of the beginning of the differential calculus, the computing this line. If it is in that factored form, especially at 0, it's this is one way to calculate that tangent line. So if you look around here, that's fairly good approximation, as you can see. Okay, there I'm showing this polynomial again, and the last 0 is this 2, so x equals 2. So if you keep that factor there and replace 2 there, that gives you 3, and 2 there, that gives you again 3. So it's 27 times x minus 2 cubed. So that's the approximately what's happening around x equals 2. So let's go to the Mathematica. So this is the picture. Notice that this time we zoomed in quite a lot. This is only 1 unit to the left, and this is 1 unit to the left to right, and this is what's happening to that part. It's changing quite quickly as soon as you go to the right by just 0.1 unit. You can see they're slightly different, but still it's picking up the behavior, the qualitative part of the behavior, quite nicely. So how exactly it resembles this one, not just that is one side is below and the other side is above. That part is not difficult to argue by looking at that how the sign changes around this point, so exactly the way we've been doing is sufficient. But exactly the shape of this one, how is the shape exactly like that, is better explained in the calculus. But if you believed our little approximation and using this monomial type of thing, and if that kind of intuitively makes sense, there's one way to understand the behavior or the shapes are near 0. So these are really called, because it was degree 3, it is indeed a mathematical is known as a cubic approximation at that near 0, and the other one could be quadratic approximation, or the case there was a straight line around 1/2 here, 1/2, that would be linear approximation, and that was degree 2 is a quadratic approximation, and so on. So I hope this example explains in quite generality that why the shapes of a polynomial functions, graph of a polynomial function near 0 behave like that. Thanks.